Hello everyone, my name is Tianshi Wang. Today I'm going to present our paper titled Audio Keyword Reconstruction from On-Device Motion Sensor Signals via Neural Frequency Unfolding. Motion sensors are widely equipped in modern smart mobile devices. Even though they have very low sampling rate, they can actually capture the vibration in the air caused by nearby human speech. And in this paper, we propose an innovative deep neural network architecture which can reconstruct human speech from motion sensor signals. When a device, such as a mobile phone, is placed on a table, the sound wave produced by nearby human speech will pass the energy through air and slightly vibrate the device. This tiny vibration is hard to be observed by human, but the accelerometer and gyroscope in that device can actually capture these signals. The major challenge we face in this project is that the reconstruction process involves recovering the lost high-frequency information. As the sampling rate of motion sensor is lower than the Nyquist rate of average human speech frequency, the motion sensor signals are under aliasing effect. Since we have insufficient sampling rate, in the waveform we perceived, the high-frequency part information will fold it onto the low-frequency part in the spectrogram. And in order to reconstruct high sampling rate audio signals from low sampling rate motion sensor signals, we need to unfold the high frequency part from the low frequency part in the short-time Fourier transform spectrogram. And this operation is called alias unfolding. Theoretically, this is an impossible task because the ways of unfolding is not unique. However, human speech has its acoustic patterns. We can use these patterns use a data-driven method to learn these patterns to narrow down the search space. So based on this intuition, we introduce an innovative deep neural network layer called Alias Unfolding. To have a closer look, the input is the sensor data in the time sequence form. Next, we pass the time sequence through multi-resolution short-time Fourier transform, and then each spectrogram undergoes a frequency convolution and then a filtering operation. The intuition of this step is to use filtering to extract the values of high-frequency parts from the original aliasing spectrogram. Then the low-frequency part can be calculated by subtracting the high-frequency part, which is the yellow one, from the aliasing spectrograms, which is the red one. And concatenating the low-frequency part and high-frequency part together, we finally have the upsampled spectrogram. The frequency resolution now is doubled. Following this, the output goes through another frequency convolution, and an inverse short-time Fourier transform brings the spectrograms back to time domain. Finally, after a mean operation, we have the final upsampled time sequence output. Here we give an example of the whole neural network framework for upsampling the input motion sensor by 16 times. Frequency expanding module is the building block of our complete deep neural network architecture, and alias unfolding layer is the key of the module. Each frequency expanding module will double the resolution of the time sequence, and after increasing the sampling rate by 16 times, the outputs of the two motion sensors are concatenated, averaging on the channel dimension, and then we finally have the output speech audio signals with 16 times higher resolution than the input. Next, to evaluate our model performance, we set up the experiment as follows. We use a Google Pixel 1 as the testing mobile device, and we tested our model on two different datasets. We have three baselines, which includes a naive approach, the state-of-the-art audio super-resolution neural network, and the state-of-the-art motion sensor signal to audio signal reconstruction network. And we use three different metrics to evaluate the reconstructed audio quality. In these figures, the red curves represent the performance of our model. It achieves the best among all the baselines in the two datasets as for the audio quality metrics. And this figure more intuitively shows the reconstruction result of our model and the baselines. The plots on the first row are short-time Fourier transformed spectrogram of the reconstructed audios, and the second row are time sequences. It shows that our model has the most similar reconstruction result to the ground truth, both in time and frequency domain, comparing to the baselines. To sum up, in this paper, we investigate the feasibility of reconstructing spoken keywords from low sampling rate motion sensor signals by using a neural network. And the key building block of the network is called Alias Unfolding layer. The experiments show that our model is superior to the state-of-the-art, but it still suffers from limitation, and we illustrate it in our paper. Thank you for your time.